So we're going to look at methane. I've got my, back to my Play-Doh model of methane. But before I even make methane, let's talk about how we make what we call a hybridized carbon atom. Okay? And so I'm going to make it a tetrahedral hybridized carbon atom. So there's my carbon atom, right, with the 4 bonds in the tetrahedral arrangement. So what happens with this? Well, we know from carbon, right, here's my periodic table, 4 valence electrons, 1, 2, 3, 4. And that's going to be 2s2, 2p2, as you can see right here. All right, so I'll call this is the atomic orbital configuration, or the electron configuration, right? Configuration. Okay, and so this process of promotion happens. So one of these electrons gets promoted up to that level. And the important thing to note here is we have 4 unpaired electrons in carbon now. Okay, and this is why we often see carbon form 4 bonds. Carbon makes this tetrahedral geometry really readily because of its atomic electron configuration. And so here, this process of hybridization, right, we just described, it's the mixing of these atomic orbitals, all right? And the new orbital that we say happens due to the tetrahedral arrangement is called an sp3 orbital. So tetrahedral, oh my gosh, I can't spell. Tetrahedral, sure, something like that. We call it sp3 because it's literally 1 s electron mixing with 3 p electrons, sp3. That gives us this tetrahedral shape. And so what's really cool about this, I'm going to go to another simulation that that we've done in my physical chemistry class. So here we go, valence bond theory and plotting the hybrid orbitals is what we call these. So lots of nasty math here that you don't have to know yet. But when we solve these equations, so all of these equations, maybe you remember that little Greek letter psi, maybe you do, maybe you don't, from our chapter 7. We didn't talk about it too much, but that gives us the wave function. So all of these equations give us the wave function. So that's basically the mathematical solution to the atomic orbitals. And what's really cool is you notice here, this totally makes my tetrahedral shape. I mean, in this model, there's nothing in here, you have to trust me, there's nothing in here that tells me to make the bond angles 109.5. We can arrive to that result qualitatively by just recognizing that the geometry, to spread out these 4 electron pairs as much as possible, they adopt this tetrahedron shape. But what's really cool, when you solve the mathematical equations given by quantum mechanics, you get this tetrahedral shape, which is really neat. So if you're interested in this, we're going to do this in my Chem 362 class that for you chemistry majors, you'll take that class as a senior. Okay, so we get this sp3 tetrahedral shape. And now, moving forward, I've got a half-filled orbital, so I've got 1 electron in each one of those sp3. Remember, we've got 4 unpaired electrons in carbon, so there's 1, and there's 1, and there's 1, and there's 1. And now in each of these hydrogens are each 1s1, so I'm drawing these arrows to represent electrons. So now, just like I showed you in that previous model, right, as I move these closer and closer together, they start to overlap and make a bond. And they make a bond because now in this shared overlap region, let me actually, let me draw these arrows in the overlap region, okay? So now we actually get an electron pair in these overlapping regions, right? A spin up, spin down electron that makes these things bond, okay? Which is pretty cool. So this is where the tetrahedral shape comes from, not only from predicting it just through simple geometry, trying to spread the atoms out evenly, but it also works with the hardcore quantum mechanics math. The math predicts it as well. So it's very, very cool, exciting stuff. Okay, so there's other ways that we can make sp3. So I want you to recognize that sp3 can really give us any tetrahedral geometry. So for example, if we look at nitrogen, so unhybridized nitrogen, that's the same thing as saying atomic nitrogen. We can see right here 5 valence electrons from the periodic table, 2s2, 2p3, okay? And so now when these things mix, what I'm going to have is 3 unpaired electrons and 1 paired electron, which is why we observe ammonia, NH3, to still have that tetrahedral geometry, except for, look, this empty stick, that represents this free electron pair, okay, which is pretty cool. So this pair right here becomes the lone pair, and now these empty 3 unpaired electrons can combine with 3 1s1 hydrogens. Let's go back to the red color, right, to give us that trigonal pyramidal shape. Remember, this is still tetrahedral, right? It still has the approximately 109.5, though we hopefully remember in ammonia, this angle is really 107 something, right, because of the lone pair. Okay, so what about water? Okay, so here we have atomic oxygen, which we know is 2s2, 2p4, right? 6 valence electrons, 2s2, 2p4. And so now when we hybridize these 4 orbitals, remember, once again, sp3 is mixing 1 s orbital with 3 p orbitals. So that makes us 4 possible geometries, 4 possible electron domains, okay? So now we can see that we've got 2 unpaired and 2 lone pairs, which is exactly what we observe in water, right? There's those 2 lone pairs, and here is my 2 hydrogens, okay? Pretty cool stuff. So they all adopt so let's draw in those electron pairs that make bonds. They all adopt the sp3 tetrahedral arrangement. However, because of their atomic electron configuration, this leads to the observation of the bent geometry, molecular geometry for water, the trigonal pyramidal for ammonia, and of course the tetrahedral molecular geometry for methane.